Hello students. Today let us discuss the topic screw thread measurements. So in this screw thread measurement we are going to learn the introduction of screw threads. Introduction of screw thread. So a screw thread comprises of a helical groove of specified cross-sectional shape. So here we can see this is a screw thread. So it consists of a helical grooves. So here these are the grooves which are formed on the cylindrical shape and they have a specified cross-sectional shape. So this is the screw thread. So this cross section of the helical groove is called as the form of the thread. So there will be minor errors arising in the screw thread measurement which have their own origin in the specification of the thread. So there will be errors when we are measuring the screw thread, and these errors are caused or they originate in the specifications of the thread. For this, that is, to check for the errors while measuring the screw threads, a terminology has been employed. Screw threads are used in fastening, and threads of this nature are simple in design and they are easy to produce. So the most common form of the thread is V, but even other variations of this form are also available. The other function of screw thread is to transmit power. So for example, we can take lead screw of the lathe or the screw gauge. So screw threads are also used in measuring devices like micrometers. So the form of the screw thread will influence the function it has to perform. So the shape or the form, the cross section of the helical groove, that is called as the form, it will affect the function that the screw thread is performing. So the aim of screw thread dimensional control is to ensure mechanical strength which is governed by the amount of flank contact rather than by the fit in the threaded hole. So we have to control the dimensions of the screw thread so that we will ensure mechanical strength, and this mechanical strength is judged by the amount of flank contact rather than by the fit in the threaded hole. So thereby we have to see that the dimensions of the screw thread are controlled. So this is all about screw thread introduction. We have discussed the measurement of major diameter of external threads. Now we are going to discuss the how we are going to measure the major diameter of the internal threads. So in measuring the major diameter of internal threads, an indirect approach has to be followed. So what is that indirect approach? So indirect approach is, so here this indirect approach is nothing but we make a replica of the screw thread by using casting technique. So this replica which we are making must be a perfect replica, and once this perfect replica is obtained, the various elements of the thread can be measured just like how we are measuring in the external thread. So material like plaster of Paris, dental wax or sulfur can be used to obtain the replicas or the cast samples. So the internal thread whose major diameter has to be measured is first cleaned thoroughly and then it is coated with a film of oil, with a thin film of oil. So the thread must be cleaned to remove the dust or dirt which is present inside it. Then after that, a thin layer of oil is coated inside the thread. Then two wooden blocks are placed on either side of the thread such that their upper part lies above halfway up the thread. So here you can see there are two wooden blocks which are placed on either side, that is on the both the sides of the thread such that they are half away. So if this is the full size of the screw thread, then these wooden blocks are placed at half away. Their head must reach half away of the screw thread. In this way, a well will be formed to receive the plaster of Paris. So here you can see there is a plaster of Paris which is placed or which is dropped into this well formed by the two wooden blocks on either side of the screw thread. So if this is the nut, it is clearly visible here. If this is the nut, you are placing the wooden blocks like this on both the sides. This is the wooden blocks. So you can see there is a well formed here which is filled with plaster of Paris. So the cast material plaster is then poured to a depth less than the radius of the thread. So the depth will be the depth up to which the casting material is poured will be less than that of the radius of the thread. Why we have to pour this less than the radius of the thread? Because it will permit easy removal of the cast without screwing it out. So after the plaster is set, it is taken out by pulling the middle portion of the cast without rotating. So if we rotate, the cast may get damaged. That is why it is pulled out by or it is taken out by pulling the middle portion of this cast. So this will result, that is the cast which we are obtaining from this method will result in a male counterpart of this internal thread. So after producing this male counterpart, we will get the external threads. So those external threads can be measured by using the techniques which we use for external thread. So this is how we can measure the major diameter of internal threads. The next one is the measurement of minor diameter. So how do you measure the minor diameter? So the best way for measuring the minor diameter is to measure it using the floating carriage micrometer. So this carriage will have a micrometer with fixed spindle on one side and movable spindle with a micrometer on the other side. So the carriage moves on a finely ground V guideway or an anti-frictional guideway to facilitate movement in a direction parallel to the axis of the plug gauge mounted between the centers. So here the carriage will move on V guideways or any other anti-frictional guideways. So why we have to move the carriage on this guideways? Because it will facilitate movement in a direction which is parallel to the axis of the plug gauge which is mounted between the centers. So the micrometer has a non-rotary spindle with a least count of up to 0.001 or 0.002 mm. So this minor diameter is measured by a comparative process. So what is this comparative process? So here we can see that there are two figures A and B. So here there is a prism. Here this is the micrometer anvil. This is the fiducial indicator anvil, and here there is one more prism, and this is value S, and here there is R1, and this is the R2 which we are measuring. So this is a standard cylinder which we are measuring on a floating carriage micrometer, and this is the screw thread whose minor diameter has to be measured. So in this method, what we do is V-shaped prisms are used for measuring the minor diameter. So the prisms of suitable sizes are placed between the standard cylinder and the instrument anvil in order to take the first micrometer reading, that is the R1. So R1 is the first micrometer reading. So after taking the first reading R1, then this standard cylinder will be replaced by the screw thread whose minor diameter has to be checked. Then readings from the micrometer are again taken. So the second micrometer readings R2 are taken when we place the screw thread instead of this standard cylinder. So how do we calculate with the help of these readings? So if the diameter of the standard cylinder is given as S, so if this is the diameter of the standard cylinder, so the micrometer readings over the standard cylinder is given as R1, that is the first reading. Micrometer reading over the screw thread is R2. So the minor diameter of the screw thread can be given as D is equal to S plus or minus the difference between R, R1 and R2. So this is how we will calculate the minor diameter of the screw thread for external threads. Now, how do you calculate the minor diameter of the internal threads? So by using taper parallel, so there are two methods for calculating the minor diameter of the internal threads. The first one is the by using taper parallels. The second one is by using the rollers. So this method of taper parallels is used for internal threads which are small. So this method consists of two wedges whose outer edges are curved and are parallel. So here there are two wedges. So these are the wedges whose outer edges are curved and are parallel. So these are the edges, they are parallel. So as the wedges are slid over each other, the diameter across the outer edge will vary and may be measured with the help of a micrometer. So here you can see this micrometer measuring anvils are placed above the wedges or the taper parallels. We can call these wedges as taper parallels. So when the edges slide over each other, the diameter of the outer edge will vary and it can be measured with the help of a micrometer. So this varying diameter will cause a reading in the micrometer, and that will give us minor diameter of the internal threads. So this method is suitable only for small internal threads. For larger internal threads, we can use the next method, that is using the rollers. So in this method, precision rollers are inserted inside the thread along with the slip gauges. So here there are slip gauges and these are the rollers, and they are placed inside the internal threads. So this slip gauges will be of suitable length such that they will not disturb the movement, or they will not allow the movement of these rollers from the internal thread, or they will place the rollers inside these internal threads. So this method is suitable for the minor diameter of the internal threads can be written as length of the slip gauges plus 2 into diameter of the rollers. So in this way we can calculate the minor diameter of the internal threads. So the next element of screw thread which we are going to study is the pitch measurement. So the effect of pitch error on the effective diameter is approximately double. So the pitch measurement must made in such a way that the other dimensions are not affected or influenced by the results in any way. So pitch measurement must be made in such a way that the other dimensions do not get affected. So the pitch can be measured in two ways. So the first way is by using the tool room microscope or the tool maker's microscope. The second way is by using the pitch measuring machine. Now we are going to learn about the pitch measuring machine. So the pitch measuring machine has different parts, that is the centers or the anvils. There is a stylus, there is pointer K, there is a base, there is pointer T, there is a micrometer, there is a spring loaded head, then there is a fiducial indicator. So here these are the different parts which I have mentioned. Fiducial indicator, pointer K, there is a base, there are centers, then there is stylus, there is a carriage which is carrying the whole instrument, there is a spring loaded head, there is pointer T and a micrometer, and this is the screw thread which we have to measure, or the pitch of the screw thread has to be measured. How does this machine work? So the screw thread whose pitch has to be measured is mounted between the centers of the machine. So these are the two centers. In between these two centers we are going to place the screw thread whose pitch has to be measured. Then there is a stylus here. So this is the stylus which is of suitable size to make contact along the thread flanks at a point near the pitch line. So here it is between the two flanks. This stylus is inserted into the spring loaded head. So here there is a spring loaded head into which this stylus is inserted. So the main principle of this method of measurement is to move this stylus along the screw thread which is parallel to the axis from one tooth space to the next, and to measure the amount of movement on the micrometer. So this stylus has to be moved in the axial direction, that is in this direction, from one tooth space to the other. So from this tooth space to the next tooth space the stylus is being moved, and this movement is measured in the micrometer. So the spring loaded head permits the stylus to move up the flank of the thread and down into the next space as it is moved along. So this spring loaded head will allow or help the stylus to move up this flank. So you can see there is a slanting flank here and there is a point here or the peak here. So because this is a spring loaded head, So spring loaded head will help, or it will permit the stylus to move up the flank of the thread and down into the next space as it moves along. So the accurate positioning of this stylus can be ensured by seeing that this pointer T is always opposite to its index mark. So if this is the index mark, the pointer T must be opposite to it when the readings are taken. So with the micrometer readings near the zero on the scale, the indicator is moved along to bring the stylus opposite the first thread space and it is clamped in position. So while taking the first reading, the micrometer, that is this micrometer, must have a zero reading, and the indicator is moved along to bring the stylus. So this indicator is moved to bring the stylus opposite to the first thread space and it is clamped in position. The indicator is next adjusted radially until the stylus engages between the thread flanks and the pointer K is opposite to the line mark. So this is the pointer K, which is here. So what next is done after we fixed or after we clamp the stylus in position? The indicator, that is this one, is adjusted radially. How it is adjusted? It is adjusted radially such that this stylus is engaging between the thread flanks. So the stylus has to engage between the thread flanks and the pointer K. This pointer K is opposite to the line mark. When the pointer is in accurate position, then only we will take the readings from the micrometer. So the stylus is then moved along to the next thread space by rotating of the micrometer and the second readings are then taken. So this stylus will be moved to the next space, that is the next in between two flanks of the next thread. How it is done? By rotating this micrometer and then we will take the second readings. So the difference between the first reading and the second reading will give the pitch of the thread. So readings are taken in this manner until the whole length of the thread has been covered. So this is how we will measure the pitch of the screw thread. The next measurement or the next screw thread element which we are going to measure is the measurement of the screw thread angle or the flank angle. See, it is important to measure the flank angle rather than the included angle, because the included angle which is between the adjacent flanks, because it is possible to produce a thread with the correct included angle but which is screwed related to normal to the axis. So the most convenient and the most common method which is used for the measurement of the angles of the flank is optical projection. So in this method, the shadow of the thread is viewed on the screen and the angles are measured by means of a protractor. So the screw thread which has to be measured is mounted between the centers of the projector. So this optical projector will include various parts which we can see here. So there is a protractor arm. This is the protractor which has the readings on the outer surface. This is the screw thread which we are going to measure. There is a pivot here. So the screw thread which has to be measured is mounted between the centers of the protractor. So if these are the two centers of the protractor, the screw thread which has to be measured is mounted between the centers of the protractor. For clear definition of the thread form on the screen, it is necessary to project the light beam along the line of the thread helix angle. To get a clear shadow of this thread on the screen, we have to see that the light beam has to be projected along the helix angle. How to do that? So this can be done by either inclining the work through the appropriate helix angle or by inclining the lamp and the collimating lens unit along the appropriate helix angle. So either the work or the screw thread which we are measuring, it must be inclined through an appropriate helix angle, or we have to incline the lamp and the collimating lens unit through the appropriate helix angle. So the protractor is supported on the screen on a straight edge, and the arrangements are made to bring the shadow of one flank into position as shown in this figure. So what is done? The protractor is supported on the screen on a straight edge. So this is the image of the protractor which is adjusted on the screen on a straight edge. So it must not be inclined, but it must have a straight edge, and the necessary arrangements are made so that to bring the shadow of one flank into position. So one flank shadow has to be brought in position along the protractor. So the pivoted arm, that is this projector arm which is pivoted, is then rotated until the edge of its shadow is parallel to that of the flank. So here this is the edge of the shadow of the flank, and it has to be parallel to the flank or the thread flank. So this arm must be rotated such that its edge will become parallel to the flank edge. Then the first readings on this protractor scale is taken. The screw which we are testing is moved at right angles to its axis until the shadow of the thread on the other side is brought in position to the protractor. So the screw or the screw thread is then moved in the direction which is perpendicular to its axis, so that the next position of the screw is brought in position with the protractor. So if this is the axis, the screw will be moved in the direction perpendicular or at right angles to its axis. So it will move like this. So after moving this in the perpendicular direction, it will be brought in position with the protractor for the next readings. So after placing the shadow of the screw in position with the protractor, the arm of the protractor, that is the pivoted arm of the protractor, is then swung and adjusted in order to measure the angle of the same flank, and the second reading is taken. So the mean of these two readings, the first reading and the second reading, we have to find the mean. So the mean of the two readings will give the angle between these flanks and normal to the screw axis, that is the angle which is normal to the screw axis as well as the angle between the flanks is the same, which is being measured by this method. This is how we measure the flank angle or the normal to screw axis angle. The next screw thread element which is of very importance is measurement of effective diameter. So the effective diameter cannot be measured directly, but you can calculate it from the measurements which have already made. So the procedure of measuring the effective diameter is same as that of the minor diameter, but here instead of using V prisms, we are using two small cylinders or wires, and these wires are inserted in the grooves of the thread. So the diameter which we are using for, if we are using the wires, the diameter of the wires must be accurately known, and when we are using two wires, the diameters of both the wires must be same. So the value of the diameters of wire can be within the permissible limits of the wire to contact the straight flanks, as well as it has to protrude above the crest. So the wires which we are using must have values, or diameter of these wires must be within range which will permit the wire to contact the straight flanks of the thread and as well as to protrude above the crest. So a correct value of effective diameter will be obtained only if the wires make contact at the pitch line. So if you want to get the correct value of the effective diameter, we have to see that these wires which we are placing between the grooves must touch the pitch line. So the wires of this size here means the wires which will be touching the pitch line are called best size wires. So the diameter of the wires should be such that they contact the flanks at a distance from the pitch line and not exceeding 1/20th of the length of the straight flank. So there are two methods for measuring this effective diameter, and they are 2-wire or 3-wire method. So the first method, that is the 2-wired method for measuring the effective diameter. So the readings are first taken over a standard cylinder with two wires in position between the cylinder and the micrometer anvils. So here there is a figure which is showing the screw thread, and there are two wires which are made in the form of a circle, and there are two micrometer anvils. So here in this figure we can see that there is a screw thread on which the wires and the anvils are placed. The same way, instead of this screw thread, we will place the standard cylinder, and then the wires are made in position and even the micrometer anvils are placed. First readings are taken with the standard cylinder. So after the first readings are taken, the cylinder is removed and the screw thread is mounted between the centers, and the second readings are taken. So from these two readings, the diameter T, that is under the wires, is obtained as follows. So from these two readings, the effective diameter can be obtained by capital E is equals to T plus C, where T is the dimension under the wire. So T can also be written as M minus 2D. Here small d is the diameter of the wire and M is the dimension over the wires, and C is a constant value which depends on the diameter of the wire, its pitch and the angle of the screw. C is the constant value. So here we can see this is M, which is the dimension over the wires. So above these wires also it is covering. So this is M. Then there is T, which is the dimensions under the wire. So T can be written as M minus 2D. So here D is the diameter of this wire. So here it is mentioned in this figure. And E is the effective diameter which has to be calculated. The formula to calculate effective diameter is given as E is equals to T plus C, where T is the dimension under the wire and C is a constant value which depends on the diameter of the wire, the pitch and the angle of the screw thread. How to calculate this C? So in triangle OAB, so here you can see there is a triangle forming here O, A and B. We can write OA is equal to OB into cosec of theta by 2. So here this angle is, if the full angle is theta, then this half angle is theta by 2. So we can write OA, that is this line OA can be written as OB into this cosec of theta by 2. So that is nothing but OB is nothing but D by 2. If the full diameter is given as D, then this value OB, that is the radius, can be written as D by 2. So D by 2 into cosec of theta by 2. And the value of AG can be written as OA minus OG. So this value AG can be written as OA minus OG. So if you minus OA and OG, we will get the value AG. Now OA can be written as this value, which is here. OA is D by 2 into cosec of theta by 2. This is the value of OA minus OG value is same as OB value, that is D by 2. D by 2. So this value can be written as D by 2 into cosec of theta by 2 minus 1, because OG is equals to OB, that is equals to D by. Now in the triangle AFD, so here there is A, this is F and this is D. AF can be written as DF into cot of theta by 2. So DF, AF can be written as DF into cot of theta by. So by assuming that the wire touches the flank exactly at the effective diameter, we can write AF is equals to P by 4 into cot of theta by 2. So here DF is equals to P by 4. So this is DF. So this is the value of P, that is pitch, and we can write DF as P by 4. It is possible only when we assume that the wire is touching the flank at the effective diameter. Now FG, this value FG can be written as AF minus AG. AF minus AG will give us the value of FG. AF is, the value is here. AF can be written as P by 4 into cot theta by 2 minus, so we have already found the value of AG, that is D by 2 into cosec of theta by 2 minus 1. But E minus T, that is effective diameter minus the dimensions under the wire, is equals to 2 into FG. So this is possible while we consider FG on either side of the thread. So this value we have to consider on either side of the thread. So we can write the value of C is equals to P by 2 into cot of theta by 2 minus d into cosec of theta by 2 minus 1. So here is how we find the value of C, because we have already written E is equal to E plus C and E minus T is equals to 2 into Fg. So E minus T value will give us the value of C. So 2 into Fg value is nothing but the value of C. So for Whitworth thread, theta is 55 degrees. So C value for Whitworth thread is given as 0.9605 P minus 1.1657 D. For metric thread, theta value is given as 60 degrees. So C value will be 0.866 P minus D. So in this way, if we calculate the value of C, then we can easily calculate the value of effective diameter, which is given as E is equals to T plus C. Or if we find E minus T, that is 2 into Fg, or that is equal to C. So this is how we calculate the effective diameter using the two-wire method. The next method is the three-wired method. So this is a very accurate method for measuring the effective diameter. So in this method, three wires or rods of known diameter are used. So how we are going to place these rods? One on one side and two on the other side. So we can see in this figure, these are the wires which are arranged on the screw thread. So one on one side and two on the other side. It will have the micrometer anvils also to support these wires. So here the parameters are like this. M, which is given here, is the diameter over the wires. E is the effective diameter which has to be calculated. E is here which has to be calculated, and M is the diameter over the wires, and small d is the diameter of the wires, which is same for all the three wires. H, that is small h, which is here, is the height of the center of the wires or rods from the effective diameter. So height of the center of these rods from the effective diameter. So if you are using a wire, its height from the effective diameter is given as small h. Theta is the angle of the thread. Small r, so this is the angle, that is theta. Half of this angle is given as theta by 2. Small r is the radius of the wire. Capital H is the depth of the thread. So this is the capital H, which is the depth of the thread. Capital D, major diameter of the thread. So now from the figure here, in the triangle A, B, D, we can write AD as, AD can be written as AB into cosec of theta by 2. AB into this angle theta by 2. The cosec of this angle. AB into cosec of theta by 2. So AB is nothing but d by 2. So if the wire diameter is given as d, then AB is half of it. So we can write d by 2 cosec of theta by 2. Capital H can be written as dE cot of theta by 2. So this H can be written as dE into cot of theta by 2. So this angle is theta by 2. So dE is nothing but half of P value. So if this is the pitch, dE is half of the pitch. So we can write it as P by 2. P by 2 cot of theta by 2. And CD can be written as, so where is CD? This is C and this is D. So the value of CD can be written as half of H. So this is the H value. So half of H will give us the value of CD. So CD can be written as P by 4 cot of theta by 2. Furthermore, the small h is AD minus CD. So value of a small h is AD minus CD. So it will give us the value of h, that is nothing but AC. So we can write small h as, we know the value of AD and we know the value of CD. So AD is d by 2 cosec of theta by 2 minus value of CD is P by 4 cot of theta by 2. So H can be written as d by 2. So distance over the wires, that is denoted by M, can be written as E plus 2H plus 2R. So this M, capital M, can be written as this E plus 2H, 2 into this H value plus 2 into the small r value, that is the radius of this wire. So we can write E plus 2 into, we know the value of small h, we have obtained it just now. So instead of d by 2 we can write r, that is nothing but the radius, cosec of theta by 2 minus P by 4 cot of theta by 2 plus 2 into r. So that is nothing but E plus 2r 1 plus cosec of theta by 2 minus P by 2 cot of theta by 2, or value of M can be written as E plus d into 1. So 2r is replaced by d, that is the diameter, plus cosec of theta by 2 minus P by 2 cot of theta by 2. So for Whitworth thread, the theta value will be 55 degrees and the depth of the thread will be 0.64 p. Depth of thread, that is the capital H value, is 0.64 p. So E is equals to D minus 0.64 p, or so cosec of theta by 2 will be 2.1657, and cot theta will be, cot of theta by 2 will be 1.921. So by using these values we can calculate for Whitworth thread the m value, that is the distance over the wire value, as E plus D 1 plus cosec of theta by 2 minus p by 2 cot of theta by 2, and this can be written as d minus 0.64 p plus d into 1 plus 2.1. So instead of E we are writing this d minus 0.64 p, and instead of theta value, or instead of cosec theta value, we have to write 2.1657 minus p by 2. So this is p by 2, it will be as it is, and then next cot theta by 2 value will be 1.921. So by this we can write the m value as e plus 3.1657 d minus 1.6005 p, where d is the major diameter of the thread. And for metric threads, the depth of the thread is given as 0.6495 p. Therefore, E can be written as d minus 0.6495, and theta is 60 degrees. Cosec theta by 2 is 2, and cot theta by 2 will be 1.732. So therefore m can be written as d minus 0.6495 p plus d into 1 plus 2 minus p by 2 into 1.732, d plus 3d minus 0.6495 plus 0.866 into, so by simplification we get this value. And for metric threads, m value can be obtained by d plus 3 small d minus 1.5155. We can measure the value of m practically, and then we can compare it with theoretical values with the help of the formulae which we have derived just now. So after finding the correct value of m and knowing the value of d, and if we know the value of m and the small d, we can find values of m and small d. So this is how we find the effective diameter by the 3-wire method. The next one is the best size wire. So what is the expression for this best size wire? So best size wire is the one which makes contact at the pitch line or the effective diameter of the screw thread. So what is the best size wire? So in other words, or in this figure, we can say the best size wire is OP is perpendicular to the flank position of the thread. So if this is the flank position of the thread, then this OP must be perpendicular to this position, that is it must be of 90 degrees. So if half the thread angle is theta by 2 is half thread angle. Then from the triangle OAP, sine of POA can be written as AP by OP. So as they are perpendicular to each other, we can write sine of POA angle, we can write AP by, or sine of 90 degrees minus theta by 2 can be written as AP by OP. So OP will become AP divided by sine of 90 degree minus theta by 2, that is AP by, when sine inverse we get cos of theta by 2, that is equals to the inverse of cos, we get sec, AP sec of theta by, as OP is equal to small r, that is small r will become AP sec of theta by 2. So here we can see that OP is the small r value, that if the full diameter is given as d, then small r will be the radius of the wire. We know that wire diameter is equal to 2r. Diameter will be 2 into the radius. So the best wire diameter is 2 into r, that is 2 AP sec of theta by 2. Because AP lies on the pitch line, we can write AP as P by 4, where P is the pitch of the thread. Therefore, instead of this AP, we can write P by 4. So, diameter of the best size wire is 2 into P by 4 sec of theta by 2. So, we can write dB, that is the best size wire diameter, as P by 2 sec of theta by 2. So this is the value for the diameter of best size wire.